When we had the metal cylinder sitting on the level surface, its weight acted, if this is a uniform cylinder, its weight's going to be right at the center of, the geometric center of the cylinder, and that's also going to be the center of mass. Its weight will then effectively act at that center. Its weight is acting straight down, and it's not exerting any torque about this point to pull it this way. Well, actually, it's exerting a torque about this point. The weight is attempting to rotate the object this way around this point of contact, but it's also attempting to rotate the object in this direction around this point of contact. Each point of contact has a force that resists the rotational effect, and the idea is simply that since the weight vector falls between this edge and this edge, this thing is not going to rotate. Now if I rotate it out slightly so that the weight vector still falls inside of the edge, whatever edge, if I rotate it this way, this edge will come up, and this edge will be my point of rotation, or the point about which the system rotates. The weight is then going to tend to rotate it back this way. If I pull it out too far, the weight is going to tend to rotate it this way, and that's what I've drawn here. We see that I've rotated it too far, and the weight vector, which acts straight down, is now on the other side of this point of contact. That means that the weight vector is attempting to rotate the system in this direction, so that in this case the weight rotates the system in the clockwise direction. If we rotated it back to where the weight vector fell inside of this point, then the rotation would be in this direction, and that pretty much explains what you saw. Now let's think about the problem of possibly trying to balance one of these Mr. Sketch markers on its end. Okay, Mr. Sketch marker again looks like this. If I attempt to balance it on its end, what's going to happen? Well, let's say I'm going to move it in this direction. I'm going to start rotating it out this way a little bit. Then it's going to tend to rotate around this point here. That's going to be the point of contact, and that's going to be the point about which the system rotates. Well, if I pull the system out to where the weight vector, which is at wherever the center of mass is in this thing, if that weight vector acting from the center of mass falls outside of the point of contact, then we're going to have a net torque around this way, and the object is going to accelerate in this direction. And of course, as it accelerates in this direction, the torque increases because the weight gets further and further outside the point of rotation, the point about which the system rotates. If I rotate it just a little bit, let's say here's the marker, and I rotate it just a little bit to here, it'll probably tend to fall back because the weight vector will still be inside this point. But since this end is fairly small in comparison to the diameter, it's not going to take much rotation to get the weight vector outside. Now if I try to balance this magic marker, or this permanent marker on its end, well, the end more or less makes a point. So any small deviation to the right, to one side or the other, is going to move the weight vector outside the last possible point of balance or point of rotation, and it's going to topple. That's why we can't balance a pointy-ended thing on its end, on its sharp end. We can't balance a pencil on its sharpened end.